So thank you very much. First, I would like to thank the organizer for inviting me to this conference. I love Sicily, and I am very excited about this conference. So thank you very much. So what I will tell you about is what physics you can do with the sun when you are located 1,000 meters underground. And as the previous speaker nicely introduced, solar neutrino physics is sort of the intersection of particle physics and astrophysics or nuclear physics. And so the original motivation for the neutrino oscillation scenario, for example, came from solar neutrinos. And our esteemed chairman came up with a mechanism for resonant flavor conversion in the sun. Then we can also directly study matter effects of neutrino oscillations of the flavor content of the solar neutrino beam by comparing day and nighttime interaction rates. So solar neutrino physics sort of brings to a conclusion the pioneering work from Sir Arthur Eddington, Hans Bethe, Carl Friedrich von Weizsäcker, and John Bacall by observing all those neutrinos in the PP chain and eventually, we hope, in the CNO cycle. So unfortunately for Super-Kamiokande, we can only see this part of the solar neutrino spectrum, and the rest of it is below our energy threshold. So Super-Kamiokande has been running for 21 years, and so far there are 4 different phases of the experiment. One with the full number of PMTs. Then there was an accident, only half the number of photomultiplier tubes, and then we completed again the detector. These are some milestones of the experiment, and in red are the milestones that affect solar neutrino physics. So Super-Kamiokande has 50,000 tons of ultra-pure water. It's a water Cherenkov detector, and we use the inner detector with 32,000 tons. And it's viewed by 11,000 20-inch photomultiplier tubes. So this is a solar neutrino event at low energy. So this is about 4.4 MeV kinetic energy. And the way we detect solar neutrinos, or the way we reconstruct them, is we use the event timing. This is a timing histogram to reconstruct the vertex. The hit pattern, this Cherenkov ring, tells us the direction, and the amount of light that we have gives us the energy. So in order to distinguish statistically solar neutrino interactions from radioactive background, we exploit the directionality of the elastic scattering process that we use for detection. So we see a very clean elastic scattering peak on top of the more or less uniform background. So this data is only from the 4th phase of the experiment. So there's roughly the same number of solar neutrino events from all the other phases as in this peak. So we can use solar neutrinos to study flavor conversion, and this was in some sense already shown by the previous speaker. So we have this, the Mikheyev-Smirnov-Wolfenstein mechanism predicts the change of the vacuum oscillation dominated regime to the matter effect dominated regime. And we have measurements at the low energy end, mostly from Boraxino, but also from the radiochemical experiments. And at the high energy end, we have, in addition to Super-Kamiokande, we also have data from the Sudbury Neutrino Observatory, and also some, with lesser precision, some data from Boraxino. So These three curves that I'm showing here differ by the delta m squared 2-1 parameter that governs solar neutrino oscillations. And so in the transition region, the turn on the transition depends on that delta m square. And the greenish curve comes from the best fit to the solar experiments only, and while the blue curve is the measurement from the Kamland experiment of delta m squared 2-1 using reactor anti-neutrinos. So as we heard, solar boron-8 neutrinos are interesting to study different solar models, and they can be used as a solar thermometer. And the way this works is one can look at the temperature versus neutrino flux here in this very old paper by John Bacall and Ulmer. And in the case of boron-8, we see this correlation with the 24th power of the temperature of the neutrino flux. And we can then use this boron-8 measurement to determine what is the temperature. And the same can be done with somewhat lesser precision with beryllium-7. And as we just heard, unfortunately, the measured data is exactly between the two extreme ends of the different abundance models of the sun. And my version of the plot was shown by Lombardini and Wynn 2017, but I agree with which it has a somewhat larger uncertainty in the boron-8 flux, but I agree with Francesco. When I do my own calculation, I also get a narrow allowed region for the boron-8 flux. But the fact remains is that unfortunately it does not distinguish between these two models. So to test the resonant conversion model, we rely on spectral information in Super-Kamiokande. And so this shows the way we extract our spectral information. We look at the ratio of the observed rate over the expected rate in the absence of oscillations. And we do that as a function of energy. And then we fit different scenarios, for example, the MSW scenario with the Kamland delta m square shown in blue, or with the solar delta m square shown in green. And we can also fit generic functions like this quadratic fit in neutrino energy, or here an exponential fit. And when we do that, then we can constrain the parameters of the quadratic fit here, for example. And we find that the points that correspond to the Kamland delta m square is somewhat less favored by our data than the one for the solar delta m square. And the difference is roughly between 1 and 2 sigma, so it's not really statistically significant. By the way, in blue are similar constraints obtained from the data from the Sudbury Neutrino Observatory. And the red contour is the combination of both. So we can look at how these quadratic functions look like as a function of neutrino energy, and then we get a 1 sigma band from SNO, 1 sigma band from Super-K. And if one combines the two, then one actually, the SNO experiment is better in constraining at the higher energy end, and Super-K is better at constraining at the lower energy end. And so the sum of both is actually more than the sum of the parts. And therefore, we also arrive at a roughly 2 sigma disfavoring of the Kamland delta m square from this combination. So how do we improve this in the future? We need to explore lower energy neutrino interaction. And a few years ago, we brought online a new trigger system at Super-K that has more than 90% trigger efficiency at 2.5 MeV kinetic energy. And this is a plot shown of the efficiency as a function of energy. So that will give us, let us explore deeper into the transition region, but we also need to worry about systematic effects. And those are mostly associated with the energy scale, with the energy response to our detector. And so recently, we have been starting to incorporate the gain variation of our PMTs. We observed that as a function of time, the single photoelectron peak, as measured by dark noise, becomes stronger in pulse height. And since there's a discriminator threshold, this will actually affect the number of hits that we observe. And we have started to implement this effect in our energy description in our description of the energy response of the detector. So if to monitor this, we use decay electron data, and we look at the average effective number of photoelectrons or photons produced. And if we don't apply a correction for this gain increase, then you see that we are outside of these blue lines, which are 0.5%. And if we take it into account, we lose about 1 hit. So this is this slight offset in the plot. But this slight increase of the number of hits goes away. So this is not fully implemented yet in our physics plots, but this hopefully will improve our systematic errors. And our energy scale is set using a small linear accelerator that injects single electrons at different points into the detector. So here we recently took, recently means the last 2 years, we took more data of that nature. Between 5 and 18 MeV. And here are just 6 positions from the previous year data, so we're still in the process of analyzing this data. And that will hopefully also improve our accuracy. And we cross-check this LINAC energy scale by generating nitrogen-16 in our detector using a deuterium-tritium neutron generator that makes 14 MeV neutrons. And we can check more positions in the detector, and we can also check the directionality, because the LINAC injected electrons are always injected downwards. So let me now switch gears to Earth matter effects. As I said earlier, we can use the solar neutrino beam to directly study the effect of matter on the neutrino flavor content. And so the way this works is we can form a rate asymmetry. If D is the day rate and N is night rate, we can form this asymmetry. And we can look for a regeneration effect if the probability of observing electron flavor is larger during the night than during the day. So this was searched for by Super-K, SNO, and Borexino. And no significant excess of, no significant deviation from 0 was found by SNO or Borexino, but there's a 2.8 sigma indication from Super-Kamiokande. And so this is the data from Super-Kamiokande. The average day-night asymmetry is something like 3.3%, and it's plotted here as a function of energy. So unfortunately, this roughly 3 sigma excess is obtained after 20 years, and that means that it will take a long time to get to more than 5 sigma significance. With the data that we have right now, this is not the full data, we expect about a 3.4 sigma significance once we analyze the remaining data, assuming that the central value doesn't change. So in order to reach 5 sigma more quickly, meaning in perhaps less than a century, then we need a larger event rate and a reduction in systematic uncertainty. And if we learn to better control background from nuclear spallation, then we have a chance of achieving both. So I showed this plot earlier. This is now zoomed in. So this is the elastic scattering peak. This is the radioactive background. And above 6 MeV or so, the dominant background comes from, it's cosmogenic, it comes from nuclear spallation. And the angular distribution shape of the background, which is not exactly uniform, is the dominant systematic uncertainty of this day-night asymmetry. So how does nuclear spallation work in water? Well, we only have to worry about oxygen. And if you have a muon coming along, usually nothing happens. But if the muon starts to shower at some point, here indicated by the X, then if the shower is purely electromagnetic, then also chances are nothing will happen. But if there's a hadronic component and it produces pions and neutrons, then we can change the oxygen 16 to, say, nitrogen 16, which then after some seconds will beta and gamma decay and cause our background. So the way we deal with this traditionally is we look at the distance of the decay product with respect to the muon track, and at the time difference and at the excess light, which comes from the electromagnetic component of the shower. And some 5 years ago, we invented a new method where we use the Water-Cherenkov detector as a time projection chamber and make a DE-DX profile of the muon track. And that helps us pinpoint where along the muon track the spallation might occur. And here's a nice example where that works. It's published in this paper by Decays et al. And so we see this excess light at just the point where the spallation decay is observed. And that helped us with our search for distant supernova neutrinos. Recently, we made further progress. I mean, when these results became known, then John Beacom and Shirley Lee produced a series of papers where they came up with a detailed Monte Carlo simulation how those hadronic showers produce spallation nuclei. And then my student actually observed this spring the neutron cloud from the hadronic showers. And so this plot here shows you the capture time on hydrogen of the neutrons that are made by the hadronic shower. And even though our efficiency of seeing those captures is very low, there are thousands of them, and so we can have a nice observation of these neutrons. And we can then study these showers. They extend to a few meters or so. This is the transverse position with respect to the muon track of those showers. And this is the longitudinal correlation of those neutrons with respect to each other. And so it's all within a few meters. So we can use then these reconstructed showers to look for the spallation candidates. And so we simply average all the positions together and look as in a sphere around that vertex of radius r. This is a plot of the distance to the third power. And we see a very clear peak within about 3 meters of that position indicated by the shower. And if you look at the time difference of those events, then we observe up to about a minute the decay of nitrogen 16, for example. Nitrogen 16 decay constant is 10.3 seconds and is quite consistent with this red line. So we hope that this will greatly reduce our dead time of spallation tagging, which in Super-Kamiokande has a muon rate of 2 Hertz, and so we lose about 20% of our data to simple accidental coincidence of solar neutrinos with one of those many muons. So for the future of day-night measurements, in principle, one can use the day-night measurement to completely deconvolve the electron density profile of Earth. And actually, our esteemed chairman produced a paper that showed that if you have good enough energy resolution, then you can see the structure, a very rich structure in both the mantle and the core of the Earth for different neutrino energies. So this is with a 0.5 MeV energy resolution on top, and this is as a function of the nadir angle eta in radians. But if you have a poor energy resolution, say 2 MeV, then a lot of the structures actually disappears as averaged out. And especially the structure in the core is very much suppressed. And so in a three-dimensional plot here we have nadir angle and energy. We see the striking difference when you have these different energy resolutions. And this is actually consistent with what we calculated for the Super-K case. We don't have much structure in the core, except when we look at our highest energies, where our energy resolution is basically determined by the endpoint of the solar neutrino interactions at 15 MeV or so. And if we go to the lower energy regions, we see integral spectra between that energy and 15 MeV. So the question is, will we get better measurements in the future from argon detectors such as DUNE or water? And so DUNE has some clear advantages. It has a tagged reaction. It has a larger cross-section per nucleus. It has a larger depth. And it has event-by-event neutrino energy, unlike Super-K. However, it also has some disadvantages. The first module, 10 kiloton, is not enough, because the event rate is only about the same as Super-K's. And so there simply isn't enough statistics. So it really needs the full 40 kilotons, and that is still a long time away. And then the question is whether the charge current interactions on argon can be triggered and reconstructed. So those are about 5 MeV electrons plus a few MeV in the excitation gammas. And so those are not easy events to reconstruct, especially because there's on the megahertz scale a background, radioactive background of argon-39. And then there might be long-lived spallation products. So the depth, of course, protects you from all of those to some degree, but the question is, well, what is their rate? So water, for Super-K, of course, the detector is really too small to see the structure anyway, but for Hyper-K, it would have enough target mass, but it only measures this integral spectrum, and so some of the structures are washed out. The differential spectrum can be extracted statistically by subtracting the various energy bins from each other. So the detector energy resolution is still important, and Hyper-K's energy resolution is going to be better than Super-K's. The ideal case, of course, would be, as it was indicated earlier, is to use salty water, doping with lithium and looking for charge current interactions. But that works best with water-based liquid scintillators, and so far we don't know yet how to produce it in sufficiently large quantities. So let me summarize. So there are still many interesting questions to be answered by solar neutrinos. So from the particle physics point of view, we want to study more the solar MSW effect, terrestrial matter effects, CPT invariance by comparing the Kamland and in the future Juno oscillation parameters using anti-neutrinos with those parameters extracted from neutrinos. And solar and astrophysics, there's the metallicity problem, solar models in general. And then terrestrial physics, perhaps reconstructing the electron density profile of Earth, and thereby extracting the chemical composition of Earth by comparing with seismic measurements. And so we can still learn a lot from Super-K data, and Hyper-K could enlarge this if the backgrounds and the systematics can be controlled, because Hyper-Kamiokande is going to be located much shallower than Super-K. So thank you very much for your attention, and enjoy the rest of the conference.
Thank you very much. Questions?